So far, we have analyzed only arguments in which the argument was in fact valid. What does it look like when we create a truth table for an argument that turns out not to be valid? Well, here's an example of an invalid argument and how a truth table helps us to see that. Here we have an argument that tells us, if you do the homework, then you will do well on the exam. You did well on the exam, therefore, you must have done the homework. Now, this argument may be intuitively appealing because of the ambiguous way that we use if-then in English. But watch this very carefully, and you'll see why it turns out not to be valid. So our premises here are, if you do well on the homework, then you will do well on the exam, and you did well on the exam. Therefore, and again we have that therefore helping us identify the conclusion, you must have done the homework. So this is composed of two simple statements combined in various ways. They are, you do the homework, we'll call that P, and you do well on the exam, we'll call that Q. Then our first premise, if you do the homework, then you will do well on the exam. That's if P, then Q. Our second premise, you did well on the exam. That's just Q put into the past tense. And then our conclusion, you must have done the homework. Well, that's just P. In the title of this page, we called this Affirming the Consequent, and the reason for that is, well, Q is the consequent, and our premise affirms it. It says that the consequent is true. Let's see what happens when we symbolize these. We have if P, then Q as a premise. And then we already have columns for P and Q, but I'm going to make a new column for Q as my second premise, and a new column for P as my conclusion. And I'm just going to put copies there to make it easier to see what I'm doing. So if P, then Q, remember the if then is false. If the if part is true and the then part is false, it's true the rest of the time. So here P is true, Q is also true, if P, then Q is true. Here P is true, Q is false, that's when if P, then Q is false. Here P is false, whenever the if part is false, the conditional is just true automatically. So when P is false, the conditional is just true automatically. Okay, and then for these columns I'm just going to copy. I'm going to copy Q, which goes true, false, false, and I'm going to copy P, which goes true, true, false, false. Okay, so to analyze whether this argument is valid, we want to look at the rows where the premises are both true. So here are my premises. In this row, they're both true. In this row, they're both false. In this row, they're both true. And in this row, one of them is false. So the rows I'm interested in are this row where both premises are true, and this row where both premises are true. In the first row, when we have P is true and Q is also true, both premises are true, and our conclusion is also true. That's fine. That's what we want from a valid argument, right? When the premises are both true, the conclusion is also true. But in the third row, where P is false and Q is true, That also has both premises true, but in that row, the conclusion is false. And we can't have that in a valid argument. So we conclude that this argument is invalid. When P is false, but Q is true, the premises are both true, but the conclusion is false. That's what we cannot have in a valid argument. So the argument is invalid. Now, the thing to note here is the argument being invalid, that's an absolute thing. It doesn't matter that there's one row that works. The only thing that matters is that this argument sometimes fails. What we're looking for in a valid argument is an argument that never fails. If we have one row in the truth table where all the premises are true, but the conclusion is false, the whole argument is invalid.